Oh, I'd like to respond to the one-way speed of light video. I think it could be measured. Let's start with a tube. This will be a side view, cutaway. So this way is up. I'll have a ball right here. I'm gonna put a clock right here. And a laser right here. Pew! Gonna do the same thing over here. Pew! Alright, gonna put another laser right here. And a receiver right here. So this laser fires off that way towards that receiver. Alright, and these lasers go to these clocks. So when the ball passes, the clock will be able to detect that the ball passed through. And one of the tricks to making this work is that from here, from that laser to this laser, is a known distance. Precisely known. All right. So, the ball will travel at a constant known speed, and we divide that distance by that speed, and that'll give us the time that it takes to go from here to here. And here's how we're going to do it. We program that known amount of time into this clock. So when this laser is tripped or broken, the clock will start counting and the ball will travel as this clock is counting. And right when the ball gets to this laser and breaks it, this clock will be at that time that we know it takes for the ball to travel that distance. And so at that point, the clock will have had the laser fire. Also, at that moment of the laser firing, this beam will be broken by the ball, and that'll tell this clock to start counting. And when the laser gets to this receiver, it'll tell the clock to stop counting. So the time on the clock will be how long it took the light, the laser, to go from here to here, the one way. And then we divide the distance by that time, and that gives us the one-way speed of light for this experiment. Cool. Now, how are we going to get the ball to go not only at a constant speed, but a known speed? Alright. Well, let's draw a chute. Same perspective, so this way is down. We'll have a trap door right here. Have the ball, let's see here, right here. And then we'll have some kind of a switch, like an electrical switch, to actuate the trap door. It'll go boom, and the ball will drop. It'll be falling by gravitational acceleration, and then it'll get to this straight part, at which point it will... Oh, did I go over the screen again? My goodness. Alright, there we go. Once it gets to this straight part, it'll no longer be accelerating. It'll be at a constant speed. Now, we got more tricks to do here. We're going to make this as close to a vacuum as we can. And that does a couple things. One, we want to measure the speed of light in a vacuum, unless you don't. You could argue that you want to know the speed of light as it travels through the cosmos, which is really, really, really close to a vacuum, but is not a perfect vacuum. maybe you would rather it match that number, but it is also nice to know what the speed of light is in a vacuum as a property of space itself, right? If you're more interested in just space, like how does that work as a medium for conducting light, you would want it to be an actual vacuum, which of course is impossible, sorry, but there you go. So whether you're trying to go for an absolute vacuum or whether you're trying to match the very, very, very low concentration of hydrogen atoms in outer space, that's a decision to make. Alright, so we're going to get that pretty much a vacuum. And that'll cut down on air resistance of this ball traveling, so it'll keep its speed, and it'll be this ball, which is a very aerodynamic shape, a sphere, to minimize the effect of the inevitable few air molecules left in there. And, of course, we're going to use good old magnetic levitation. So, I'll draw some imagined cubes here. I know they don't really look like cubes. Alright. We can say that these are neodymium magnets. And we'll say that this ball is made out of a superconductor. So like a ceramic, a special ceramic cooled to its critical temperature. And how that's special is not only will that magnetically levitate, it will be locked into this track and it will remain a fixed height above the magnets. Had we instead done, North Pole repulsion or South Pole repulsion, so for example, if you had two hollow shells, two hemispheres, and you put a bunch of magnets in there on both sides, on both hemispheres, where all the north poles were facing outward and all the south poles were facing inward, and then you stuck the two halves together to have a ball where it's all north outward, and then had all these magnets be north upward, so that it's north on north to magnetically repel. If you did that, that'd be out of control. It would in no way be locked onto the track. That could be a serious issue. Now, with it being a superconductor, you get those nice properties of control. You could have even put the magnets on top and had the ball hang below them, because it would keep that fixed distance from the magnets. Now, maybe it would be more affordable to do electromagnets. I did a quick Google. It seemed like neodymium magnets would be cheaper. Also, to consider what's more consistent. Would a whole bunch of supposedly identical neodymium cube magnets be a more consistent field than a whole bunch of electromagnets? Maybe. And if you need to get some of your money back, because this isn't going to be cheap to build, how well could you sell back or sell into the market neodymium magnets versus electromagnets? Be an interesting question to look into. Alright, so we got this chute here. I want to revisit that. So there's going to be a bunch of neodymium magnets, right? Or however we're doing our repulsion. Yeah, push that paper up. See the magnets. It's going to be all along the bottom of this elbow. So because this is a superconductor rather than... I've got to make this flat again. Because it's a superconductor repulsion, instead of north-north or south-south, this will stay a fixed distance from the magnets all the way through this chute. Whereas if this was north-north or south-south, the ball would just fly off, or it'd run over to the right side. It wouldn't remain fixed because we're no longer opposing gravity here. This is going down. Alright, so that gets it to a constant speed. The vacuum, the levitation, and the chute all together achieve constant speed that every time you drop it, it's going to come to the same speed each time. But how do we get that known? Alright, Here's a way we can do that. The first time the ball goes through, we can have the clock run a different program. We'll measure the diameter of the ball, and we'll tell the clock to start counting once the beam is broken, and then stop counting once the beam resumes. So the distance traveled will just be the diameter of the ball. So that distance, the diameter, divided by the time on the clock will be the speed of the ball. Alright. Another part to remember, so this is constant, you don't want to move the chute. Once you set it up, keep it there. You can make it maybe not quite as vertical if you bump it, and if we want to be really technical, where you have it over the earth can have a different amount of gravity to it based on what's below it. I mean, we're not in control of like magma currents or plate tectonic movement or anything, which could technically change the density of what's below it and therefore the gravitational acceleration, but that's pretty out there picky. We'll just say build the chute and don't move it until you're done with the experiment. Alright. So, it's at a constant speed and it's known. It's a known speed. What if this method of determining the ball's speed gets deemed imprecise, and why might that be? Okay. We'll zoom way in on the chute here. Okay. We'll say this is the front of the ball. Back half of the ball is symmetrical to the front part of the ball. Of course, I didn't draw that as a perfect portion of a circle, but oh well. Okie dokie. Okay, I haven't finished the drawing yet. This is the width of the laser, and this is going into the clock, or the receiver of the clock. What's the rest of the picture going to look like? So, is it just going to be this thin portion that keeps shining by, a nice, totally straight thing, because it's a laser and not diffused light? Or maybe is the laser going to shine through a really, really thin portion of it that is thin enough to shine through, and then by going through that, it becomes diffused light again, so now it's going to go like this instead of staying. I guess I'll do a dot, dot, dot. Like maybe does this action right here. And so the lasers are going this way. And then we got, this option. And then a maybe something going as a dotted arrow. I don't know how well you can see that. Maybe. So maybe that way. I don't really know. I don't know. Now, getting more to the point here, does this detector have a bias? Does it actuate and say that's a read just as soon going into the beam as it would coming out of the beam? Because remember, we're detecting two different things when the beam is broken and when the beam resumes. So how far in the beam does it have to be for detect that it's broken? Does it have to break 100% of the beam, 99% of the beam, 90% of the beam, 50% of the beam? I don't know. Let's say it was 50%. Alright, now when the ball's gone forward, now the back half is coming out of the beam, so part of the beam is going and part of it's blocked by the back end of the ball. Is it going to be 50% there also, or does it have a bias for breaking over resuming or resuming over breaking? That maybe one's 50, one's 40, one's 90, one's 10%. I don't know. So should that be the case, let me give you an alternative. Okay, I'm going to have a new diagram. This will be a change in perspective. We're going to be looking down on top of the track now. So we got our ball whizzing along here. Okay, try to draw that in the center of the track, whereas up here, you know, it's down low because we had clearance for the laser. So the laser will be going over it, except in this instance we won't be using the laser, this one. I'm just saying that for sake of perspective. Looking down on top of it. Alright, now I'm going to try to draw a circle. A little eggy. How am I doing here? Not bad. Okay. Alright. Bump the thing here. Alright, so let's at the center of the track there, or the center of the circle. This is the track. Let's draw a straight line from that. Put a clock right here. Put a laser right here. Okay. So this laser is going to shine to this clock. So the ball is going to go, and when it breaks the laser, the clock will start counting, and then the ball will go around. So when the ball left the beam to resume the beam, the resuming part is not a tick to record. It's going around, and then it breaks the beam again. That's when the clock stops. And so the clock started and stopped on the same kind of event, breaking the beam, as opposed to one event being break and the other being resume. So whether it's 90-10, 25-75, or whatever, as we were talking about over here for breaking versus resuming, doesn't matter because it's breaking both times. It's just consistent with itself. So that'll give us the amount of time it took to go around the circle, and of course the diameter of this track will be known. Let's refer to that as 1 unit, but that's 1 foot, 1 meter, 1 whatever. This is 1, that's not a 1, that's a 1 unit. Okay. It is measuring the diameter from the center of the track to the center of the track on both sides. Okay. Now, a little bit of physics here. We know that to change direction requires energy. This ball has inertia, it has momentum, it wants to go straight, and we're causing it to change direction. So that inertia has to be overcome. And the only energy we have to pay with to afford for that, or to pay for that, is the speed of the ball. So this will slow down to have fought that inertia. But the energy does not leave the system. It's kind of like compressing a spring. The spring is no longer in motion, but it's holding energy, or putting a ball at the top of a cliff. You know, there's potential there. And it turns out that you only have to slow down once, and then once you've slowed down, you stay at that speed around the circle. So the circle is consistent. It's the same curve all the way around as opposed to an egg shape. So we have that same amount of energy opposing the pushing in by the track. And so it keeps that constant speed around. And then if this were to open up and we had like a straight section to go into, like a little door here, and then went straight again, then it would resume its original speed. That potential energy would come back as kinetic energy. Alright. Yeah, for every action, there is an equal and opposite reaction. And when an action halts, so too does its reaction. So the action was changing the direction of the ball, and the reaction was that it slowed down. So if you remove the action, it's no longer having its direction constantly changed, then so too does the reaction. The reaction also goes away, which means it speeds back up. Alright. Now that may seem like a bummer because we were interested in the speed of the ball going straight, and we're measuring the speed of the ball going in a circle, right? We got the time off the clock, and we divide this distance by that time to get the speed. What about the straight distance? I'll have to put a link in the description to credit the video where I learned how to do this. It has been figured out how to mathematically compute what the straight speed is. So let's just draw the quarters of this circle here. Alright. So if we had another chute like this, and we had another ball the same mass, everything was identical except one path went straight and one was this. Alright. What would happen is for every quarter circumference that this ball goes, the other ball would travel one diameter. Alright, so the ball in the circular path travels 1/4 of a circumference, which is 1/4 pi units, for every time that the ball in the straight path goes one diameter, or 1 unit. So that's our ratio, which of course equals pi quarters. So if I multiply the speed of the straight ball by pi quarters, I get the speed of the circular path ball. Or I can just divide the circular path ball's speed by pi quarters and get the straight one. Or multiply it by 4 over pi if you like your pi upside down. Alright. Now remember, so we don't want to move the chute, right? We want to keep it over the same part of the earth and not like bump it and make it any less vertical or anything. So you'd have to like connect it to this and then disconnect that and then connect it to this one. Alright. So let me use my cheat sheet here so I don't forget anything. You should see my code. Just kidding. So how are we going to keep this level? Good question. One idea I had was maybe put it on a frozen lake and have that act as a natural water level. Maybe. The other thing I wanted to point out was that pi, being an irrational number, is not a problem. It may seem like, oh, well, we're inherently introducing imprecision because we're only using a finite number of digits of pi, so that is necessarily not exact. But think about this. Say you picked a number at random off the number line. It is infinitely more likely to be an irrational number than a rational number. Okay. So suppose the speed of the ball and the speed of light that we're trying to measure has random speed. Random relative to the information we have. You know, we don't know what its speed is. We're measuring that. Okay. Now, our devices that are measuring the speed of things, the timing and all that, they're only precise to so many digits. So if you use more digits of pi than what you have, and then the precision of your devices, you're not losing any precision. You know, it's infinitely more likely by the logic I was describing before that the speed of the ball is an irrational number, which is an interesting thought. And we're only getting a finite number of its digits. Alright. Now another thing, what if there's like weather in space itself? Let's go with this. So how do we know that the laser didn't go one speed from here to here, another speed from here to here, and another speed from here to here? We're just getting the average velocity of it traveling in that direction. Like, what if different patches of space are sort of flowing different directions or have different favorances, you know? I've heard an analogy that space is kind of like a crystal, that it was liquid at the Big Bang and then it crystallized, and you could have cracks in that crystal called cosmic strings and yada yada. Well, maybe if it's like a crystal, some parts are oriented one way and some parts are oriented another way. I don't know. You know, maybe, oh, look at this. So if you have the sun here, the Earth here, and Mars here, say this patch of space favors from Earth to Mars. So a light traveling from Earth to Mars is faster than from Mars to Earth. And then as the planets go along the orbit, in their orbits, maybe in this patch of space, the favorance is to go from Mars to Earth. And then maybe as the sun goes around the galaxy, we hit other patches, and maybe as the galaxy moves through the cosmos, we hit different patches that way. Yeah. Something to think about. I don't really have a particular reason for thinking this that way, but I don't really have a particular reason for thinking that the speed of light would be different one way than the other either. You know, we're talking about what can be measured experimentally here. Also, thought I'd share my setup here. I was just using a shoe rack. Mom told me I should get a shoe rack, and it turned out to be really useful, so there's some mom advice. Alright, I hope we can continue this conversation. Hope you have a good one. Bye.